So today I want to talk about Shor's factoring algorithm. It's probably going to take, almost certainly going to take more than today. We'll continue tomorrow. But to start out, I wanted to introduce the problem of factoring and explain why it's an important problem. So factoring. You might be able to guess from the name what I mean by the problem. So we're given some n, big N, which is pretty big. And the goal is to find two numbers, p and q, greater than 1, of course, such that n is equal to pq if p and q exist. And usually, actually, restrict it a bit further, and you just happen to know that n is the product of two prime numbers. So p and q then are the primes factors. And of course, this question of do p and q exist, are there non-trivial factors, that's the primality testing question, which, as I told you, was it last time or Monday, is in P. So there is a good algorithm to tell whether there exist prime factors. But to actually find them, that turns out to be hard. So there's a decision version of this, which is equivalent. So a decision problem is mostly what I've been talking about so far, where the answer is a single bit, yes or no, right? So this problem, as I phrased it, the answer is you can't answer it with a single bit, right? You have to give, well, you have to at least give one of the two factors, right, which is many bits long. But the decision version is given two numbers n and m. And then the yes or no question is, does m have a prime factor less than big M? OK? And the reason, certainly if you can answer this question, you can answer this question, right? You just find the factors, and then you know whether they're bigger, whether they're both bigger than M or not. But if you can answer this question for arbitrary n and m, or really for n and arbitrary m, then you can answer this question. Why is that? Well, first you say, OK, let's let m be square root of n over 2. OK? And if it doesn't have a prime factor less than square root of n over 2, you say, OK, what about 3/4 square root of n? And so if it does have a prime factor that's less than 3/4 square root of n, then you've narrowed it down to between square root of n over 2 and 3/4 square root of n. And then you can narrow it down again by looking at, by asking, what about 5/8 of square root of n? And so on, right? And so you're narrowing it down by cutting the space of possible prime factors in half each time. And how many times do you need to do this before you've narrowed it down to the exact factor, or at least a very small range where you can just divide in? Well, that's log of big N times, roughly. Right? And so that means that if we have so the input size here is also log of big N, right? That's the number of bits you need to write down n. And m is obviously going to be less than big N. So it's still O of log big N. So that means that if you have an efficient algorithm to do this, that means it's something that's polynomial in time log of n. And well, doing this, subdivision gives you another factor of log n in there. So it's still polynomial. So an efficient algorithm to do this implies an efficient algorithm to do this. OK? And this problem is in NP. Why is it? Well, remember, NP is the complexity class of of problems where there's a witness that lets you verify that a problem is, in fact, a yes instance. I guess I didn't explicitly say this, but NP has this asymmetry where if it's a no instance, if there doesn't exist a factor, or it doesn't exist a witness, you don't have to be able to prove that. Right? So you can only check the yes instances. Anyway, factoring, it turns out, there's witnesses in both ways, so that's a little more complicated. But so does n have a prime factor less than m? What's the witness for that? Well, here's the factor, right? And then you can easily divide that into n and see that it really is a factor. Okay? And so that underlines the other side of this, which is if you're given P and Q, that's easy, meaning there's an efficient algorithm to it, right? You learn that in elementary school. But the reverse problem of factoring seems to be hard, right? Certainly, there's no obvious way to do it, right? You could try a bunch of different prime factors, but again, that's an exponential algorithm. And you can do much better than that, but nevertheless, and in fact, people have worked really hard to find good algorithms for factoring for reasons that I'll get to in a minute. But nevertheless, the best publicly known, maybe I should say, again, for reasons I'll get to in a minute, factoring algorithm takes about x of log n to the 1/3 steps. Okay, so that's not quite exponential in the input size, but it's sub-exponential. And it's certainly more than any polynomial. Okay, and the upshot of this is that in practice, today we can factor maybe 500-bit numbers on the biggest computers. I'm not sure what the current state of the art is. But much more than that is just totally out of reach. OK? Any questions so far? Yeah?
Is this related to RSA cryptography?
Yes, that's what I'm going to say next. But any questions on what factoring is? Yeah, this part should be straightforward. So OK. So indeed, the reason that factoring has been the subject of intense study and the reason I said publicly known algorithms is because factoring, the hardness of factoring, so there's a cryptographic system known as RSA, which is a public key crypto system, and I'll tell you what that is just in a minute, depends on factoring being a computationally hard problem. And if you could factor numbers efficiently, then you could break RSA. And so cryptographers, of course, really want to see if they can do that. And so there's been a lot of work on that. And of course, various intelligence agencies spend a lot of money in private trying to come up with better factoring algorithms. So it's quite possible that, say, the NSA has an algorithm that's better than this. I think most people believe there's not a polynomial time classical algorithm to do it. But that, again, there's a lot of space between polynomial time and this, right? So you could certainly improve on this substantially and still not have a polynomial time algorithm. OK, so what's a public key crypto system and what's RSA? So the general setup is we want to send an encrypted message. So we have Alice and Bob, who actually originally were cryptographers before they got into quantum information. And Alice wants to send a message to Bob. But there's an eavesdropper, or she believes there might be an eavesdropper, Eve, that's listening in. And so Alice wants to make sure that Bob gets her message without Eve learning it, even though Eve is listening in. And of course, the standard way of doing this is to encrypt the message. Right? Alice and Bob have some key that they use to encrypt the message, and so Eve can't learn it. So in a symmetric crypto system, Alice and Bob share the same key. And that's fine. That there's various symmetric crypto systems that are more or less straightforward. But they have this problem that Alice and Bob have to get together to share the secret key, and they have to keep it secret from Eve. Okay? So public key crypto systems are a lot more flexible and widely used because of that. And the idea in a public key crypto system is that there's a public key that Alice has that she's using to send the message, and a private key that Bob has that he's using to decrypt the message. And the thing about the public key is because it's only used to encrypt the message and not to decrypt, it's OK if Eve learns E. Right? So Alice doesn't really have to be careful with this public key. She gets it from Bob. And in fact, she might get it. Bob could give it to everybody that he knows. Put it on his website, put it in the footer of his emails, things like that. Publish it in some public directory. The eavesdropper certainly has access to these things. But it doesn't help her. Knowing the encryption key is not enough to learn the private key, and it's not enough to decrypt the messages. Okay? So this is much easier to manage the keys than in a symmetric encryption scheme. And we'll get back to that next week when we talk about quantum key distribution. Okay, so there exists various classical public key crypto systems, and they usually rely on some kind of computational assumption, and RSA is no exception. And the assumption is going to be that there's some computationally hard problem that Eve cannot solve. And because she can't solve that problem, she can't figure out D, or even figure out how to decrypt messages in some cases, right? So that means that Alice and Bob can be sure that Alice's messages encrypted using the system are secure, provided Eve does not have more computational power than they expect. So normally what we want when we say the problem is hard is that it's outside of P, right? That it's exponentially hard. But of course, in practical terms, that's not enough. It might be that it's super polynomial, but still it grows slowly enough that Eve can for certain key sizes can break it. So you have to be sure that you set your parameters big enough so that you really are kind of more in the regime where it's out of Eve's computational power. OK, so RSA is the best-known public key crypto system, and it's very widely used. It was invented by Rivest, Shamir, and Edelman. That's why it's called RSA. At least it was publicly invented. It turns out it was also invented by the British, I forget what it's called, but the British Information Security Agency in the like a decade or more earlier, but nobody knew about that. OK, so here's how RSA works. So what we have to do is we have to come up with a way of finding this E and this D so that you can't really figure out D from E, but you can generate them together, and that they have this right relationship between encryption and decryption. So here's the key generation step. So Bob is going to have to do this. He's going to generate, because he's the only one that knows D. So he's going to generate E and D together by picking two large primes. And then we're going to let n be the product of those primes. And so Bob then will also choose some E less than n. And then finds a D. Let me just say finds D such that x to the ED is equal to x mod big N for all x. OK. And how he does this is based on some number theory that I'll get to in a minute. But the key point is that doing that, generating that relationship between E and D, involves his knowledge of these factors of n, big N. OK? And so if somebody else were to learn those factors of big N, they would also be able to find D given E. But only Bob knows that, so that's his advantage. OK? And once he's done that, then the private key is going to be D. And the public key has two parts, actually. So it's big N and E. OK? And then how do you do encryption? So suppose Alice has message X that she wants to send. She wants to send to Bob. So what does she do? She calculates. So this is called the ciphertext that she generates. Ciphertext Y is x to the E mod n. OK? And you see she can do this using the public key information of big N and little e. Right? And the time it takes to do that is just something that's kind of polynomial in the number of bits of the various numbers that's involved. OK. And so suppose she has a longer message. Well, what she could do, she could break it up into segments, each of which uses log n, big N bits. And then send it in blocks like that. The actual way it's done is a little more complicated. And I'll mention why in a little bit. But so for decryption, so Bob receives some ciphertext Y. And then he calculates Y to the D mod n. And well, we know that, assuming the message hasn't been altered, and this doesn't protect against that, that Y is equal to x to the E. So this thing here is x to the E times D mod n. And we picked E and D so that x to the E times D is equal to x mod n. So Bob has recovered the original message. OK? Does that make sense?
can we find D? Is it related to the phi and the...
Sorry, how can we find D from E?
Yeah.
Yeah. So right. So that's the missing piece. So for that we need Euler's theorem. So this is a kind of a central and, for number theorists, fairly basic result. So it says for all x less than n, x to the phi of n is equal to 1 mod n. So what is phi of n? Phi of n is the number of, so it's called the totient function. I have no idea why. And it's equal to the number of natural numbers less than n and relatively prime to n. So obviously, when n is very large, like thousands of bits long, going through and exhaustively counting everything less than big N is not a way to figure this out. But it turns out that there's a straightforward formula for phi of n in terms of the factors of big N. So first of all, notice that if big N is prime, then the answer is easy, right? It's just big N minus 1, because everything less than it is relatively prime. So it turns out when n is equal to pq, and p and q are primes, then phi of n is equal to p minus 1 times q minus 1. OK? So Bob knows p and q, and therefore he knows phi of n. So why is this important? Well, so when Bob picks E, he should pick it to be relatively prime to phi of n. And of course, if he just picks it randomly, there's a large chance that will happen because, well, I guess that's not necessarily true. There's a constant chance that will happen. But he doesn't have to do that. He knows this phi of n, so he can be more careful when picking E. And then using Euclid's algorithm, which you saw in the tutorial, he can find some d such that dE is congruent to 1 mod phi of n. Right? So this is a different version of the formula that you had. You said that there were two numbers that were relatively prime, and so you can find coefficients of the two of them so that the sum is equal to 1. Right? But that's really what this is. Right? This is equivalent to saying that dE is equal to 1 plus, let's say, c times phi of n. So you see that's the form that you were working with Euclid's algorithm. OK? And then once we've done this, you see that when we take x to the ed or to the dE, we can write it this way, but then every factor phi of n is equivalent, x to the phi of n is equivalent to 1. So x to the 1 plus something times phi of n is just x. OK? So once we've done this, D has the property that we wanted. So are there any questions so far in RSA? So do you all feel like you could go home and write a program that would do this? So even if you do feel that, you probably shouldn't. And the reason is because, well, first of all, there's a couple of things that I guess didn't tell you how to do. Like, you're supposed to pick these big primes. And one way to do that is just to pick some kind of random numbers. And primes are not so rare that if you pick a bunch of random numbers, you'll eventually find a prime. But in order then to know that it's prime, you have to do this primality testing algorithm, which I didn't tell you how to do. The other thing is that there's actually a lot of art in how you implement this. So it turns out that if you're not careful about how you pick P and Q and N and E, then it might not be a hard instance of factoring. It might be a relatively easy instance. An easy example is if P is not big, right? If you just pick like 3, right? Then if you happen to know that P is relatively small, you can just try dividing by some small primes until you find it. Okay, so that would obviously be a bad thing to do. But there's other cases in which it's straightforward. And I mean, in the real world, they also want to pick E and D so that the encryption and decryption are, efficient, not just in a theoretical sense, but in a practical sense, and as efficient as possible. And then there's another big thing that I didn't tell you, which is suppose this eavesdropper Eve has a pretty good idea of what message Alice is going to send. Right? She may have narrowed it down to just a few possibilities. The thing is, the way I describe this public key crypto system, Eve does know the encryption key. And so if she has only a small list of possibilities, she could just try encrypting all of them using this scheme, right? And compare to the ciphertext. And if one of them matches, well, she knows that that was the actual message. Okay? So this is not, as I presented it, this is not secure in that sense, this scheme. So the way you actually use this in the real world is Alice doesn't send her message directly with RSA. Instead, she generates some random bit string, some random number, and encrypts that using the ciphertext, using this method, using RSA. And of course, since it's a random number, Eve actually has no idea what it is. So she doesn't have this option of attacking it by trying a small number of possibilities. And then Alice sends that to Bob, and Bob and Alice now share this secret random number. And then you use that long random number as the key for some symmetric key crypto system that doesn't have the same kind of vulnerability. Okay? And that's how it's actually used in practice. Yeah?
So is that a C in the last line?
1 plus C times 5n. It's just, it doesn't really matter. It's just the point is that's what mod means. Anything else I want to say? Yeah, okay. So are there any other questions on RSA? Okay. So having done all of that, we're almost but not quite ready to talk about Shor's algorithm. But now there's kind of a little bait and switch, because I said that Shor's algorithm is a factoring algorithm. That's certainly what it's widely known as. But actually, that's not true. Shor's algorithm is an algorithm for period finding. So here's the problem of period finding. So we'll have some function which now is going to take the integers mod n to the integers mod n. And this function is periodic. With period r. And I want to make the extra constraint that it doesn't repeat otherwise. So in particular, f of A is equal to f of B if and only if B is equal to A plus some multiple of R, C times R, say. Okay, which has nothing to do with that C over there. Okay? So this is periodic because every time we add R, we get back to where we started and then continue from where we started. Right? So if the outputs are 5 and then 10 and then 30, once we get to the period, we get 5 and then 10 and then 30 again, and so on. And the period finding problem is then to find R. Okay? So this problem at first glance doesn't seem to be closely related to factoring. But it turns out that if you can solve this period finding problem, you can solve factoring. So there's a reduction from factoring to period finding. I don't think there's a known reduction in the other direction, in general, certainly. So yeah, I could say that about RSA. So if you can factor big N into P times Q, you can certainly break RSA, right? Because that's the information that Bob had to generate D from E. And so knowing big N and knowing E, if you can factor big N, you can also derive T. But it's actually not known for sure, although people believe that they're equivalent. Right? So it might be that there's an algorithm for breaking RSA that doesn't tell you how to factor numbers. That's possible. Okay, so how do we get factoring from period finding? So in particular, we want to find the period of this function, fx of A, which is x to the A mod n. And we want to be able to do this for an arbitrary x. Okay? So first of all, why is this function periodic? Well, it's the same Euler's theorem, right? If we take x to the A plus phi of n, that will give us back A. Yeah, so it could be, of course, that it has a smaller period in some cases. Is that true? Actually, I'm not sure. But that's not exactly how the reduction goes, although it's close. So how are we going to do this? Well, our goal is to find x that has even order. And it turns out that if you pick x's randomly, then with some constant probability, constant probability that a random x will have even order. So if you just pick some randomly, calculate their orders, after a few times, you'll probably get one that's even. And then once we've done that, we let y equals x to the r over 2. Okay? And so now we know that y squared is equal to 1 mod n, which implies, maybe let's do it up here, which implies that y squared minus 1, which of course you can factor to y plus 1, y minus 1, divides big N. Sorry, other way around. Is a multiple of big N. Okay? So why is that useful? Well, N, remember, is P times Q. And so this thing on the left-hand side, the P and Q are prime. So there's a few possibilities, right? So one of them is that they're both factors. They have to divide somehow into these things. So they could both be factors of y plus 1, in which case n divides y plus 1. That's one possibility. Or it could be that they're both factors of y minus 1. Or it could be that p divides y plus 1 and q divides y minus 1. Okay? So let's go through the three possibilities. So the easy one is this one. We know this is not true. Why? Why do we know that? Because this would imply that y is equal to 1 mod n. But r was the period. So there's not going to be a smaller value that gives us 1. And in this case, we know that y is minus 1 mod n. And that can happen, but it's easy to check for. And so if we did happen to get that, we found something that has even order, and we multiply and we get minus 1, then we say, oops, let's try again. And it turns out that, again, with constant probability, you can find an x that doesn't have that work. Yeah?
So what is order?
Oh, yeah, so order is the period of this function. So order is the smallest r such that x to the r is equal to x mod n. Right, was this? Yeah, sorry, x to the r is equal to 1. OK, so we've eliminated these two possibilities. So we're left with this one, right, which we can get some constant fraction of the time for over random x. So suppose p divides y plus 1 and q divides y minus 1. And specifically, we've ruled out these cases. So we know that q does not divide y plus 1, and p does not divide y minus 1. So what's the GCD of n and y plus 1? Well, it's p. And the GCD of n and y minus 1 is q. OK? We know y plus 1, we know y minus 1, and we know n. And so again, using Euclid's algorithm, you can find p and q. OK? Yeah.
It's not possible to have y equal to minus 1.
Oh, it is possible. It is possible. But if you guys pick random x's, well, sometimes you will get odd order and it won't work. Sometimes you'll get even order and it'll be y equals -1. But with constant probability, if you pick a random x, you'll get something that is even order and y is not equal to -1.
So this only works when we have even order.
Yeah, so because we needed to take y as x to the r over 2. So if r is not even, you can't do that. So okay. Any other questions? Yeah.
Question about RSA, like here we choose only 2 primes. Like there's nothing forbid us like to choose more primes, like choose 3, 4, 5.
Sorry, choose more whats?
More large prime numbers and then multiply them.
Oh, that's not generally a good idea. I mean, you could still make this work, right? I mean, there's a formula for the Tolkien function, and you could do that stuff. But the thing is that by choosing more primes and multiplying together, that given big N is the same size, that means the primes have to be smaller, which makes it easier to solve. And with more primes, it means more factors also makes it easier to solve. So that's why people like to pick 2 big primes, just because that's kind of the hardest case. Anything else? Yeah.
So, I mean, so this is actually not a, it's kind of related to the prime. Like, is it true that if someone discovers a large prime, that has to be reported to the government or something like that? Or?
No, I don't think so. I mean, the size of primes that we're talking about for RSA are not really exotic. In the sense that, I mean, the whole point of it is that your computer can quickly check whether this number is prime or not.
Right.
Okay, so when you see a news story of somebody's discovered some large prime, they mean way bigger than this. Much bigger. Okay, any other questions? Now, I mean, there have been all sorts of things about crypto where governments sometimes want some sort of key escrow thing so that they can break people's cryptography, but that's a totally separate question. Okay. So let's get to Shor's algorithm, get back to quantum. So what Shor's algorithm does is it solves this period finding problem. And we're just going to apply it to this particular function. But you'll see that that's not incredibly important. There's kind of only one aspect of this function that is really relevant, which is that you can compute it quickly as a function of the number of bits in A and big N. Yeah, but so you can apply it to other types of periodic functions, and for instance, it's useful for breaking some other kinds of crypto systems, and has other applications as well. But I'm going to focus on the factoring application. So okay, so here's Shor's algorithm. So we're going to have 2 registers. And they're going to start all at the zeros. And then we start out like we did with the Lecture6 algorithm by doing the Hadamard on all qubits in the first register. And then we're going to calculate this periodic function. So so x is given, and this register is going to be our A register to start with. And so we're computing x to the a mod n down here. And then what we're going to do is we're going to measure the second register. And then we do the Fourier transform. Write that out. And then we measure these qubits. And then there's some classical post-processing. That gives us R. OK? So let's see. So this this Fourier transform is the mod n Fourier transform. So here's what it does. So if you apply it to a basis state A, it gives you sum over b omega to the ab b, where omega is the, sorry, it's not the mod n. It's mod 2 to the little n. Omega is 2 pi I over 2 to the little n. And you can think of n as kind of very roughly log of big N, number of bits. But actually, it's longer than that. And I'll explain why probably tomorrow, why it has to be a little bit longer and kind of roughly what it should be. Right. And just to be explicit, this thing here, this x to the a mod n unitary is taking a, well, you can think of it as a unitary. It takes a times something here to a c plus x to the a. And all this arithmetic is done mod n. Yeah.
So what is A and B in the Fourier transform? Are they like?
Yeah. So these are just the, we're taking little n bits here, and so this is the label. A is the label for the basis state. This is a unitary. I'm describing the whole unitary behavior. So these are the basis states are labeled by bit strings A, and then the output is going to be some superposition of bit strings, and I'm labeling those by B just for convenience.
I guess I'm just wondering the power omega AB. So there's a power. Is that
omega to the a times b? Yeah. 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 So this multiplication is mod 2 to the n because omega is 2 pi over 2 to the n. So if you have a factor of a term 2 to the n here, it just gives 1. Okay. So this is just kind of the definition of things, and this is what the circuit is going to look like. So if there's any questions on, not about what it does, I'm going to talk about that very soon, but just the structure of it. OK. So then let's once again go through step by step and see what it does. But I'm going to do some simplification because the real case is a little complicated. So anyway, so same idea. This here will be step 1. And at this point here, that's going to be step 2. And then this point here is step 3. Sorry. This point here is step 4. this is step 5. Step 6 is this measurement. And then the classical post-processing will be step 7. OK, so the simplification I want to make is we're going to pretend that R divides 2 to the n. OK? And actually, in the cases that we're really interested in for factoring, that's never true. So, so this is definitely an idealization. It's unrealistic, but it lets you see how this algorithm works much more clearly. And then tomorrow we'll get into the imperfect, the real imperfect case when R does not divide 2 to the n. OK, so step 1. Well, that's easy. It's just everything's 0. So we have our 2 registers, all zeros. Step 2, we've done the Hadamard on the first register. So remember from yesterday, that means that the first register has become sum over A of all possible A's. OK. And then the third step, well, we calculate x to the A and add it to the third register. We started 0, so it's now this. Entangled between the first and the second register. OK? This part is straightforward. Next step is where it starts to get interesting. So the measurement result, so at step 4, we're measuring this second register. So suppose the measurement result is z. And so that's x to the a for some a. But it's actually x to the a for more than one a, because x to the a plus j times r is equal to x to the a. This is mod n. Because r is the period, right? So x to the r is 1, and x to the j r is 1. So that means that z is also equal to x to the a plus jr. And so conditioned on this outcome, the state is this. Sum over j of, here, let's this be x to the a0. And these can be x to the a0 here. So then this is a0 plus jr. We have all possible a's that are consistent with this z that we found here. The other ones have disappeared. The state is collapsed, but it's not a complete collapse. There's still a superposition left. OK, and then I guess I can put z here, but now I'm going to kind of ignore this. OK, so everyone got that? OK, so then step 5, Fourier transform. So we're starting with this state, sum over j, a0 plus jr. And so the Fourier transform will give us, well, let's see what happens to this particular basis state under the Fourier transform up there. Chalk is running out of ink here. No, OK. So sum over b, we get omega to the a0 plus jr times b, right? And we can switch the order of summation and kind of reorganize this. So, so this is equal to sum over b. So let's take out, we have a thing here that doesn't depend on j. So we have omega to the a0b. And then we have the sum over j. Well, what do we have? So I'm going to substitute the value of omega back in there, e to the 2 pi I over 2 to the n. But then I want to rewrite it. So it's 2 pi I. So we have omega to the jrb. So I'm going to write it 2 pi I jb over r over 2 to the n. Sorry, 2 to the n over r. so this r is on top, right, because we're dividing by dividing. And so that's what we had over there. And this thing here is summed, and then we have b. OK? Everyone with me so far? OK. So so what do we do now? Well, so this thing here is a sum of the form e to the 2 pi I jb over alpha summed over j. Now, if b over alpha is an integer, so if alpha divides b, then this is just, every time this is just, for any value of j, this is just 1, right? And so we have to sum over the number of different values of j we have, which it turns out there's alpha of them. So what happens if a does not divide b? Well, if a does not divide b, this is not an integer. And so say when k equals 1, it's some root of unity that's not 1. And then we're taking that to different powers, right? And when we do that, these multiples of a root of unity get spaced evenly around the unit circle. And when you add them up, you get 0. So that means when alpha does not divide b, the sum is equal to 0. OK? And so what that means is that this sum is going to kill out all values of b that are not a multiple of 2 to the n over r. So we can do that. So we're going to be left with a sum over c. And we're going to let b be equal to c times 2 to the n over r. So this is this. And then the ket is, again, c over, c times 2 to the n over r. OK? Got it? So that was the key step. OK, so once we have this, well, then step 6, we measure it. So the measurement results will be, one of these values. We have a sum over different values of c. So we'll get one at random. OK? And so then the post-processing, I guess it's maybe not fair to call it classical post-processing. So we're going to repeat this process a few times. And so after we've done that, we've gotten c1, 2 to the n over r, c2, 2 to the n over r, c3, 2 to the n over r, et cetera. And if you look at GCD, again, of these things, so remember, in this case, 2 to the n over r is an integer. So we're dealing with all integers here in this idealized case. With very high probability, the only common divisor of all of these things will be 2 to the n over r. It would be really bad luck to keep getting multiples of the same constant c every time we do this. OK? And of course, once you know 2 to the n over r, you know r. that make sense? OK, so one last thing today then, which is just a very simple observation. So the way I describe this, at step 4, we measured the second register. But if you're paying attention, you notice we didn't ever use that information, right? So you don't actually have to measure that second register. That's not important. That's not really actually part of the algorithm. But it is very helpful for analyzing the algorithm and trying to understand what's going on, right? Really what's happening is you have a superposition of different values of z here, but they're entangled with the second register. So when you see the measurement result, you do the Fourier transform, you do the measurement result down here, it's just like you had picked some random z. The z doesn't disappear, right? It's in this A0. But this is a phase. And when we measure it, that phase doesn't affect the result. OK? So what's really going on here, did I draw this? I did not draw it. So OK, what's really going on here, I should have drawn. So at this point here, we have, if you think of this as the ket in the register, we have a superposition that looks like this. OK? These are spikes separated by r. This first one is A0. And so we have these periodic spikes. And of course, the Fourier transform pulls out the periods, right? And so the Fourier transform is therefore telling us, sorry, these are not separated by r. These are separated. Oh, yeah, these are separated by r. So the Fourier transform is going to give us multiple spikes again separated by a period. But now the period is 2 to the n over r in the idealized case. OK? And this initial shift of where the first thing is, that becomes a phase. Again, that's what the Fourier transform does. OK? Does that make sense? Yeah.
How can we implement the Fourier transform using elementary K?
Yeah, very good question. So tomorrow I'm going to talk about that. I'm also going to talk about how to do this modular exponentiation. And I'm going to talk about what happens when r does not divide 2 to the n. So, but yeah, doing the Fourier transform, definitely not obvious how to do that. And that's an important part of the algorithm. Any other questions? OK. So yeah, like I said, tomorrow we'll finish talking about Kerr's algorithm.